All right, so in this video, I want to go over kind of how we make different compounds. So taking it beyond just like, individual atoms, how we can look at the electrons of them and all of that stuff, but how we can actually like connect those different atoms. So to begin, I guess we should get to like why exactly it is that, different atoms and elements will even want to, I guess, connect with other ones and why they would want to create compounds. So right, kind of the general idea here is that if we think back to like the noble gases, right? The noble gases are named as such because they're royalty in the different elements. Noble gases have, these added stabilities in having like a complete valence shell or 8 valence electrons, and most other elements and atoms want to look like a noble gas then. They want that full shell. There are, of course, exceptions to the rule as always, but generally speaking, right, most of our different, especially main group atoms, they have like this goal in mind to have these 8 valence electrons. And so this is referred to as the octet rule, right, making like a group of 8. And what we're going to focus on first in this video is ionic bonds specifically. So an ionic bond will form when you have, say, an atom that has beyond 8 electrons. So maybe something like sodium or potassium, right? They have just like one extra valence electron they don't want, right? If they could just get rid of that, then they could look like their nearest noble gas. So maybe one of those types of atoms is going to give their extra electron to an atom that maybe has just under that 8. So thinking about like chlorine or bromine, right, where they have just one electron short of a noble gas, right? If they can pair up and find an atom that is looking to give away an electron, then those two are going to be happy with one another. It's kind of a visual here to show maybe this relationship occurring, right? We can consider lithium and fluorine, and so I have both their electron configurations and their orbital diagrams shown on the left. Again, lithium is one of those atoms that starts off with just like one too many electrons compared to its noble gas. And fluorine is one that has just one too few electrons. And so what this figure illustrates is how a lithium atom can give away its electron to a fluorine atom, thus completing fluorine's valence shell and leaving lithium with just that inner core. And so, right, when we make these ionic compounds, we start by forming these ionic bonds. It's really just this transfer of electrons that occurs here. Now, to get a little bit further into the energetics of like how these different compounds are made, I want us to call back like way far into Chem 161 when you guys are learning about like, say like Hess's law and thermochemistry, right? These should be ringing some bells. I want us to consider like the formation of solid lithium fluoride, and thinking about the energetics of like how all these different pieces may fit together to make this solid. As a little bit of a spoiler, right, I looked up the formation of solid lithium fluoride and found that that is an exothermic reaction. So, right, that will end up releasing heat as part of that formation. And right, we can kind of think about this formation in different steps and different pieces and see how they all add up together. So first, I want us to consider, kind of the things that we talked about before, taking our maybe original elements, lithium and fluorine, and turning them into, say, the ions that make up lithium fluoride. So first, for the lithium, right, because we want to take lithium and turn it into a positive ion, we're going to need its first ionization energy, which here I found is 520 kilojoules per mole. And again, I've written out the equation here just to kind of show, right, how chemically these different pieces are changing. And so taking 1 mole of lithium gas and turning that into 1 mole of lithium plus gas, and thus leaving an electron out, right, that's associated with that first ionization energy. Now we can also consider then taking the fluorine and making that into its F minus ion. So that would require then the electron affinity of fluorine, which here is negative 328 kilojoules per mole. And so if I think about these, two pieces kind of as part of this formation of my lithium fluoride compound, right, making my lithium plus and my F minus, right, basically the energy associated with these two parts together should just be the sum of those energies that I showed before, right? So thinking back to Hess's law and how if you have, different steps in a reaction, energy itself is a state function. So you can just add the energy of those individual steps together, and it should give you then the overall energy of the whole process. So for this case, right, if I have plus 520 kilojoules minus 328 kilojoules, that should leave me with like a net amount of 192 kilojoules. And just looking at that, I'm kind of a little bit surprised because, as I said at the top of this slide, right, this formation of lithium fluoride should be an exothermic reaction. It should release heat. And again, calling back to like Chem 161, y'all should know that an exothermic reaction has a negative energy change associated with it, right? It's losing energy. And so to see this positive value right here tells me that I'm missing something. And I'm actually missing like quite a few things. So let's dive in and look at really all of the pieces that go into making this ionic compound. So again, combining my electron affinity and my ionization energy does not seem to be giving me a complete picture of the formation of lithium fluoride. If we recall back to, I think, chapter 9 in Chem 161, we should recall that like a formation reaction, like making lithium fluoride, that should be done in what's called the standard state. Now by standard state here, we just mean like, how those elements traditionally occur at like room temperature. And so if I look at my periodic table, I see lithium should be a solid at room temperature. So already my equation that I have up here is not really fitting that. Additionally, we know that fluorine is one of our diatomics. So instead of just like F, as we saw in the electron affinity, we're going to have actually like F2 kind of worked into here as well. So to really complete our formation reaction, we're going to need a couple of additional steps included in here, not just that transfer of electrons, but also, making sure that our elements themselves are actually matching like what we would see in the real world. So that would involve kind of taking our elemental lithium or, solid state lithium and turning that into a gas to match with the ionization energy. This is referred to as the enthalpy of sublimation, or delta H subla, right there. We're going to dive into that particular phrasing later on in the course, but it's basically just the energy or heat that it takes to take a solid and turn it into a gas, like we would with this lithium here. Additionally, because the fluorine, being diatomic, needs to be broken up into these different, individual fluorine atoms, that's going to have a certain energy associated with it here. This is referred to as the bond dissociation energy, or really 1/2 of the bond dissociation energy. So that D refers to the amount of energy it takes to break apart two atoms, right? Or the amount of energy it takes to break a bond. This we'll also learn about later in class more specifically, but right, just to give us like a little sneak peek into the different steps energetically that take place in formation of an ionic compound, right? This usually must happen as well. But so now, if I take a look at these different steps that I've all put together, I'm going to see something again that's a little shady because, right, both of these additional steps here are also endothermic. They're also adding more energy. So already my problem was that like what I had before was not exothermic. Now it seems like things are just getting even less exothermic. And so I'm like, how is this formation of lithium fluoride supposed to be exothermic if these individual steps are not? And the reasoning behind this, kind of the big explanation here, is all about these charge-charge interactions when a lithium ion and a fluoride ion actually meet. So right, those positive and negative ions are super duper attracted to each other. And so they are going to start pairing up. And they're not just going to pair up like one lithium with one fluorine and they make like a neat little molecule. Instead, they're going to pair up into this repeating lattice structure, making like a solid crystal. And each of those lithiums is going to be surrounded by fluorines, and each of the fluorines is going to be surrounded by lithiums. And so there's a ton of charge attraction that is going on here, and those attractions, right, bring the energy down. It stabilizes everything because now the lithium is not flying all on its own by itself. The fluoride is not flying all on its own by itself, right? They're all coming together and being held in place through these attractive forces. And so it's this attraction that brings down the energy so much, right? Taking a lithium plus and an F minus and actually putting them together into this solid state crystal, that drops the energy, as we can see right here, as negative 1050 kilojoules per mole. So it's this amount that is like hugely stabilizing, and that's what's going to cause then the overall process to be negative. This energy, not itself, but actually as the like reverse version, is referred to as the lattice energy, or U. This is the amount of energy it takes to take like a solid ionic compound and bust it apart entirely into its individual ions. So separating it into both lithium and fluoride and putting those into the gas phase. So like completely obliterating your crystal structure. That is how you get the lattice energy. So the lattice energy itself is actually the reverse of this like coming together process. Lattice energies by default need to require a lot of energy in order to do them, right? In order to break apart your crystal structure, you're going to put a lot of energy into that. And that's what's represented here as U. And so now putting all of that together, right? When we consider things like a compound being made from its component elements, so that is like the formation of a compound. Specifically for ionic compounds right here, they can be broken down like so. So my overall process that I'm looking at is really in the black line, going from solid lithium and fluorine diatomic gas, turning that into lithium fluoride, the solid, right? So that is my overall enthalpy of formation. But what that's actually made up of, or what that actually entails, is basically like 5 steps, right? You're going to have the step of, say, taking the lithium and turning it into a gas, so that like sublimation step. You're going to have the step of breaking apart the fluorine molecules into fluorine atoms. And then you're going to have these like ionizing steps, right? Taking, say, the lithium and turning it into lithium plus through its ionization energy. And for the fluorine, turning that into fluoride or F minus, right, through its electron affinity. And then finally, those ions are then going to cluster together through the negative of the lattice energy. So that's what's shown there in step 5. All right, so this is all referred to as the Born-Haber cycle. Really, the Born-Haber cycle is just like a way of showing the different steps that go into an overall process. I believe it originated from like the production of ammonia or something, so something like completely different from what we see right here. But right, this Born-Haber cycle is just like a way of showing each of the steps involved in some greater reaction, right? So really it involves like a lot of little pieces, but they do kind of merge together into one overarching thing. Now I want to give you guys just like another example maybe that you can try to work through as far as using the Born-Haber cycle. So here I want for you to determine the lattice energy, or U, for sodium hydride. And I give you a bunch of thermodynamic, values and things from the textbook or whatever else, right? You see things like the enthalpy of sublimation, enthalpy of formation, all of that stuff. And so putting this together, right, I want you to find that missing piece, right, the lattice energy for sodium hydride. I'm not going to actually like work it out in this video or in this example. I think I'll probably just go over it in class with you guys because I want you to have like a little bit more practice with it. But if you want to try to take a stab at this on your own, and then we'll look at it in our next class period, then that would be like super awesome practice for you. All right, but so maybe as like a little challenge, right, try to see how you could piece these different things together, and then we'll talk about it later on, because it's like kind of complicated to like draw it out in the PowerPoint and like the video, and so I just don't really want to do it in the video format. But I do want to show it to you in case you just want like a little extra to do here, but I'll just walk through this or a similar example in class on Monday. But so to close out here, I want us to just kind of consider that last bit, that lattice energy portion of the Born-Haber cycle, and kind of think about, again, like more holistically, like what's going to affect the lattice energy, say, of an ionic compound. And so really at the heart of this is Coulomb's law. If you've taken like an electricity and magnetism course, you're probably familiar with this idea. It basically will relate like the positive and negative charges of ions that are attracted to one another, as well as the spacing between them to represent then just like how stabilizing the energy is going to be with it. So Coulomb's law can be represented right here, where F is force, K is just like a constant, and then our different Z values here are the absolute value charges of our different ions. So for instance, if you've got like magnesium 2 plus and chloride with minus charge, then Z1 and Z2 are going to correspond to those charges. So like 2 for magnesium and then 1 for chlorine. Then the D here just refers to the distance or separation between our different charges. And so traditionally speaking, that's just like the ionic radii of your different ions. And so lattice energy itself is kind of related to Coulomb's law through this relationship. It's basically that force, that attractive force, times distance. So what we're left with here is a calculation for lattice energy that just includes that K constant and then our charges divided by the distance alone. Now we won't actually like use this equation. I just wanted to show it to you to show, how things like charge and distance kind of relate or affect the lattice energy that we use in the class. Just thinking about it more like holistically and more as like a matter of proportions, right? We can kind of generally say that the lattice energy is proportional to the charges times each other divided by the sum of your ionic radii. So again, thinking like more generally here, right? If you were to compare something like lithium fluoride versus magnesium oxide, right, which of these do you think would have, say, like a higher lattice energy? Now, I'll note that, unless you have like the actual ionic radii right in front of you, I don't necessarily expect you to know the precise numbers for the ionic radii. There are, of course, different trends and things, but as it turns out, for these two compounds, the lithium plus fluoride radius is about the same as the magnesium and oxygen one. So don't necessarily worry about the radius portion of this, I guess I should say. All right, so hopefully you've thought about that for a moment and decided which of these two guys is going to have a higher lattice energy, not going based off of radius, but instead just based off of charge. I think it becomes pretty clear that something like magnesium oxide, that's going to have the higher lattice energy, right? Because magnesium is 2 plus and oxide is 2 minus, right? That portion of the fraction is going to be much greater than for the lithium fluoride, which just has single charges on both of its ions. And so with that, right, we can kind of say, again, most generally, affected by these different factors. Now, something that I want to point out, especially as we, start thinking again about like proportionalities and things, for this particular example, right, I said that like the summed radii are basically the same between these two compounds. There will be cases where they're not so close, but honestly, the range for ionic radii is relatively slim, right? So what I mean is like even like your biggest ion versus your smallest ion, there's, some variation in that, but it's not like usually that huge or that large of a factor. Things like charge, though, can have, hugely impactful changes going like across the periodic table by one column, right? So like a one charge, like a +1 charge versus a +2 charge, that's a factor of 2. Like that's literally double. That's huge. And so I would say that the charge element of this proportionality is probably more important than the radius one. But if you are, say, comparing between a bunch of compounds that do all have the exact same charge, so in this case, I've got lithium fluoride versus sodium chloride versus potassium bromide versus rubidium iodide, right? With these ones, we can then focus a little bit more on the radius itself. So when the charges are entirely all the same, it doesn't really matter, right? The top part of this proportionality. The only thing that's really important here is the radius differences, and right, that will help us decide what the lattice energy is then. So right, when it comes to kind of I guess, making the decision on which factor is more important, I would say that charge kind of takes precedence, and then radius and distance comes into play if the charges are already all the same. But so now looking at these four examples, which I just previously listed, which of these do you think will have a higher lattice energy? So go ahead and take another moment to think about this, and then I'll explain it in just a bit. All right, so looking at these guys, again, these all have just +1, -1 charges, pretty boring, whatever. So what we need to rely on here is the radius sizes. And as we look at our proportionality, right, what this is saying is for U, our lattice energy, what would favor, say, a higher U would be a smaller summed radii, right? Because that is in the denominator on the other side here, if I have a smaller number in my cation plus anion radius, that will then translate to a higher lattice energy. So of these guys, right, the ones with the smallest radii have to be lithium fluoride, right? That includes elements from literally just the second row of the periodic table. As you move further down the periodic table, radius keeps increasing and increasing. And so really lithium fluoride here is going to be kind of our star in a way. To put this into another little graphic, just to compare these guys, right, I have here just the lattice energy of many different compounds or different combinations to make different compounds. And so as you can see, right, something with a smaller radius is going to have then a higher lattice energy. As you get to these much larger, more cumbersome ions like rubidium and iodide, right, those bring the lattice energy way down. Because those ions are so big, it's like their charge interactions are going to be much weaker, right? They're not able to like hold on to each other as well as the little guys can, just because like the charge density is so spread out. But so please let me know if you have any questions. We'll tackle one of those Born-Haber cycle questions on Monday in class. And if you do have any questions, I'm always happy to help.